Today we are going to, today and the next lecture and last lecture will be devoted to deformation, the part of infinitesimal deformation theory, and show you how much can be done without actually using the spaces, with just working with sets. That basically the idea is that the reason I want spaces is that I want the infinitesimal picture pointwise to glue together nicely in a nice global structure. At the same time, it is good to know that we can understand the punctual description, because in general, a morphism of derived schemes will be an isomorphism or an equivalence, which means they will be the same if the non-derived structure is the same, and it's an isomorphism on all tangent spaces. So this means we cannot recover. There is more information in the derived schemes than there is in the underived scheme and the collection of infinite tangent spaces at every point, but it's still a lot. So if you basically, it means that once you know that the derived scheme exists, a lot of information about it can be squeezed out just from underived moduli and infinitesimal derived structure. So let me start by recalling that in classical deformation theory, you have this category of Artinian local algebras, and you study functors to sets. And there is a nice criterion that guarantees for you that ideally you would want your f, the best is if f is so-called pro-representable, and which means that it is induced by a complete local C algebra with some additional finiteness assumptions I'm not going to spell out, but this basically means that our R is the limit of the quotients by the powers of the maximal ideal. Notice that if A is in Rt, then its maximal ideal is nilpotent, which means that if we want to consider homomorphism from R hat to A, in fact, this be equal for n sufficiently big. And basically the finiteness I want is that all this finite approximation also be Artinian. And there is a criterion, and of course the first condition for this is certainly we always assume that f of c is 1 point, as we did until now. And there are Schlesinger conditions that are equivalent to pro-representability. Necessary and sufficient conditions for pro-representability. And in particular, these conditions take the following form, that if you have morphisms in Rt, and of course what you get from this, Rt is a category with fiber products, so you can do this. And because f is a functor, you get such a morphism. Let me call it eta. And the conditions we want is essentially that under suitable assumptions, eta is what we want. Some of the conditions are that eta is surjective if A to C is surjective, and eta is bijective if C. Let me not say explicitly in some additional assumption. In particular, if C is C and A is C plus C epsilon with epsilon squared is equal to 0. And we notice that this condition here is, I told you that we could define on F of, sometimes I'll just write it like this, a vector space structure, and I hadn't told you how you define the sum, but now this is clear. Let me for a moment. What you get is you have a map from F, if you call this A, you get a map from A cross CA to FA cross FA. I would have to do the fiber product over C, but the image of C is 1 point. And this is bijective. And on the other hand, I have a map here which is introduced by the sum. So A times CA is C of epsilon 1, epsilon 2, such that epsilon 1 squared, epsilon 2 squared, and epsilon 1, epsilon 2 are 0. And these maps sends epsilon 1 to epsilon and epsilon 2 also to epsilon. And now this is bijective, so I can invert it, and this is the addition. And we already defined the 0 and the scalar multiplication, and the other Schlesinger assumption is that this tangent space be finite dimensional. I am slightly cutting some corners, but basically that's the idea. And so now the goal is to bring as much as possible of this over to the art, which I will also define in one moment. And in particular, this topic has been studied a lot by a number of people, but because this is a school, I will not give you the historic approach and all the different definitions. Instead, I will follow one exposition chosen because I like it and because the author is a friend, which means he explained it to me, which is extended deformation functors by Manetti. And I want to point out the date to show you that higher tangent spaces were already around and can be defined. This is one paper, but again, it refers to a number of previous papers. So higher tangent spaces are not an innovation of homotopical derived algebraic geometry. They were there in infinitesimal deformation before that, which doesn't mean we want them to become global, but they are not new. Okay, so now what we want, remember, instead of working with the whole generic structure, we want to just work with sets. So the first thing is what we take as the art And we will take local differential graded algebras with residue fields commutative, with residue field C and total finite dimensional as C vector spaces. You can ask yourself, do we want to put a limit on the degree? So do we want to insist that they are in non-negative, non-positive degree? And the answer is that this depends on which reference you take. In the reference I'm following today, no, we take arbitrary degrees, but in other references, what you typically do is you either do what we saw, that we directly put all the degrees non-positive, or we do a compromise, as somebody also asked, and you can require that the grading be positive and negative, but there be no cohomology in a positive degree. And where we want to do is we will want to define a notion of a deformation functor. So go from this D art to sets, which will have the following. It should be seen as the infinitesimal description of a derived moduli space or stack near a point, just as the original deformation, just as the original classical deformation functors describe classical moduli spaces. And in particular, such a deformation functor will come with higher tangent spaces. We'll have higher tangent spaces. And again, we have to decide which will be functorial, because of course, if you consider deformation functors, which are just functors, there is no higher category going on, although as you will see in a minute, some higher category will come back in a minute. But so far, this is just a category, this is a category, and so all the functors among them are a category with maps which are natural transformations. And these higher tangent spaces will be functorial. So this again is the typical thing we want when we do deformation theory. We want to make sure that not only the map on the tangents is natural, but the map of the obstruction is also natural. And we will want that if we take such a deformation functor f, the ith tangent be f of c plus c of epsilon to the I, which means I put epsilon in degree minus I, and I also insist on these two conditions. So this is exactly what Mauro had proposed for us. And here again, there could be a shift by one. Again, as I told you, there are these two traditions how to index the higher tangent spaces, and I am not going to be precise about that because this is not so important. It's just a matter of how you call it. On the other hand, there is one point which we haven't discussed yet, but luckily was introduced today, which is the notion of differential graded Lie algebra. And here we know what this is. It's you know, a complex with a bracket, and the bracket satisfies satisfies graded Jacobi equation, and it's skew symmetric graded, and it behaves well with, you know, compatible with the differential. So it's like a differential graded algebra, except this time our model is not a product, not a commutative associative product, but a Lie bracket. And whenever we have a graded Lie algebra, in a number of contexts, it becomes natural to work with the Maurer-Cartan equation, and we shall see that to every such thing, we will be able to associate a deformation factor which will have Ti is Ti such that Ti of the deformation is, again, up to shift by 1 the ith cohomology of the Lie algebra. So I think there is a shift, there is a 1 difference between here and here, and I will not fix it now because it's all written down. And I want to, in particular, yeah, so this is kind of the picture, and eventually the idea is here, in Schlesinger pro-representability, we had the notion that we can control our deformation problem by a formal power series ring, essentially. And here we control our deformation problem by a differential graded Lie algebra. And this differential graded Lie algebra is no longer unique, but it is unique up to quasi-isomorphism. And sometimes we say that it governs the deformation problem. So the idea is we do not work with these with spaces, we just work up to homotopy, and we still can get information out of there. Just as we did in classical deformation theory, when we work with stacks, we have values in groupoids, which are very, very simple spaces with only P1 groups and all higher homotopy groups vanishing, but we still can recover information. And so let me try to set up the conditions.
I'm sorry.
Yes.
In classical deformation problems, what is L?
There isn't. That is the point, that classically you have this theorem of pro-representability. And then today I will give one example of L, and then Thursday we will see more. The point is that they are typically, this description very often comes up in complex analytic geometry, actually. So I wanted to have a bit of a bridge to the, today I will give an example in algebraic geometry. But the fact that Maurer-Cartan equations are important, I think, is well established. But today I'm not talking about that. Let me focus on what I have prepared, because if I try to go out of order, I'm not going to end well. Yes?
What is the cohomology means, HIL?
Well, this is a differential graded Lie algebra, L. It's a complex with a Lie bracket. So in particular, it's a complex, and so it has cohomology. Sorry, the question was what is the cohomology of a differential graded Lie algebra? And differential graded Lie algebra is a complex with a bracket. And so I can always, like we did for differential graded algebra, I can always forget the product in one case and the bracket in the other and still take cohomology because I still have a complex. And here I want instead to start defining stuff. And you can see that now I really have to make sure because this is a bit technical. In fact, I told you that here I want to work with sets, while naturally here, as I explained this morning, here the morphisms are naturally simplicial sets, Kan complexes. Yeah, I have because I have these simplicial objects inside differential graded algebras. And so if I want to work with sets, the least I can do is I can try to see what happens if I replace a map by a homotopic map. And so typically, one thing you do, remember, eventually we want to invert quasi-isomorphism. And one of the things you can do to invert quasi-isomorphisms is to identify homotopic maps. Because once you invert quasi-isomorphism, homotopic maps automatically become identified. And so what I can do is definition, let A and B, and for the moment just be in DGA, differential graded algebras, and F and G from A to B, some homomorphism. And we say that F and G are homotopic, and this really means their image in the pi 0 of the simplicial set of all higher maps are the same. If there exists an H from A to B. So what do I mean by this? Remember, this used to be C of T0, T1, dt0, dt1 modulo T0 plus T1 minus 1 dt0 plus dt1. And now I've just shortened by declaring that T is T1 and that T0 can be recovered by the equations. And such that, so now I have my A, this goes with H to B, turn B off if you want, T dt. And now I have two compositions. In one composition I map T to 1, and then the other composition I map T to 0. And in either case I map dt to 0, and I go to B, and I want that the two compositions are F and G. So they are really homotopic in the sense we described today. So notice that on a topological level, what we are saying is that we have two maps, X, which corresponds to B, and Y, which corresponds to A, and we want that there is a map from X times I, that I have X which goes via 0 and via 1 in X times I, and this goes to Y. So this corresponds to H, and we want So remember, we always want that our algebra have arrows going in the opposite direction as they would in a geometric context. And just as with complexes, one can show that we can define a category K of the art, and in fact also K of DGA, whichever we want, with the same object and however defining the morphisms, but morphisms are homotopy equivalence classes of morphisms. And when I say we can define, it means we basically have to repeat the proof we know in the topology case to show that if two maps are homotopic and we compose them with another two maps which are homotopic, then also the compositions are homotopic. And this is in some sense, if we want that our functor is induced by our functor to spaces, the first minimal condition we want to have is that it factors via. Once we go back to sets by taking pi 0, it must have the same image over homotopic maps. So in some sense, it's a very minimal condition. And now we have to introduce some definition. And the first definition is that of a small extension. And this is the usual one in the art. And this is the direct copy. It
Sorry,
says,
I have a question.
yes.
Sorry, in the middle of your definition. But the notion of homotopic here is different from the notion of homotopic of two chain maps, I guess.
yes,
Right? So
yes,
that
it is
homotopy
different.
will be also different.
Yes, this is the natural so the point is that if you have a homotopy for chain maps, this comes from, so let me see if I understand the question. So the idea is that if I have a complex and another, so a chain map means vertical arrows, and a homotopy is something that goes this way. And you can see, that was not the smartest move in my life, but if you look at what this does, the H, it sends something into this T. Yeah, no, I understand. So it's not exact. No, it's not the same. But it's something that, you see, with homotopies, it works also the other way. That if you have a map and a homotopy, so something diagonal, then you can add it and you get back another map. And the problem is, what condition do you want to put to ensure that the new thing you get respects products? And this is something which is not clear to me. And so this way, but this reminds you of something I should have said and did not, so this is very important, is that, moreover, the HI from d art to vector spaces, so if I have a differential or DGA for that matter, to vector spaces, factors via K of DGA. This is absolutely important. So it has the same property. The one we do like this, the first thing you prove when you do the zigzag is that the induced map on the cohomology groups is the same. And this one has exactly the same property. So it's as close as it can be, but making sure that we preserve the multiplication structure.
Thanks.
Okay, so what is a small extension? Is a surjective map such that the kernel satisfies MA times I is equal to 0. So this is exactly the same definition as we had in a non-derived case. But now we can add one condition, which is small acyclic is small plus the cohomology of I is 0. So, or in other words, small plus alpha is a quasi-isomorphism. So we have now what used to be one condition, this basic block of understanding deformation theory, which was small extensions, comes in two ways, where this one says basically that the kernel is close to be 0, is homotopically 0. So in this case, we really expect no change from A to B. Okay, and now we come to, remember our goal is to define a notion of deformation functor, which will be analogous to that of pro-representable functor. But before we get there, for instance, as I told you, even in the case of the Schlesinger assumption, some assumption is used even to state the next. And in this case, we are in a similar situation. So definition, a pre-deformation functor f from d art to sets is a functor such that, and now I have conditions. And these I really need to copy because they are a bit technical. Of course, the first condition, as usual, is that this is one point. This is the classical thing. And the second, I will use exactly the same notation as I have before. And so it will be eta, let me call this 0, because this is really before the mole. And one is eta is surjective if A to C is surjective. So exactly the same one have. And moreover, we want that it's eta is bijective if A to C is surjective, and let me say it informally, C is C plus a graded vector space. So this is an informal condition, but the formal one is an acyclic graded vector space. And by this I mean that MC has MC squared is equal to 0, so there is no multiplication, and the cohomology is also 0. And finally, I have a last condition. And the last condition is that for any acyclic small surjection A to B, as in the sense I just gave, the map f A to f of B is surjective. So this is just a big definition, and exactly like the one by Schlesinger, it's just something that you see and it plants itself on your stomach and you don't understand why. So the point of this very dry definition is that you want that it has good consequences about, on the one hand, you want enough assumptions to be able to say a lot of things about this functor, and on the other hand, you don't want too many assumptions so that you have a lot of examples. And let me make an example. One, that if R is a quasi-free DGA, local DGA, sorry, do I need local? Yes, a quasi-free DGA with a chosen MR local. Let me not write this. Where is my eraser? So I will, this is kind of a quasi-free local. This has a technical definition which I'm not going to give because every time I try I get it wrong, but it should be the equivalence of a formal power series which is free as formal power series, but then it has non-trivial differentials. And then what you have is that HR from the art to sets given by, just as before, HR of A is Hom R A, which, remember, this is also equal to some quotient for n sufficiently big, but the n depends on the A, Just like in the non-derived case, this is a pre-deformation functor. Okay, so this is kind of the preliminary work. And another work is that to let, and here we come directly, so let L be a differential graded Lie algebra, and we can associate to it its Maurer-Cartan functor. And the Maurer-Cartan functor goes as follows. First of all, you can take L tensor over C with MA, and this has a natural structure of graded Lie algebra, differential graded Lie algebra, where the notion, the way it's a complex, it's clear, it's a tensor product of two complexes, so we know how to make it into a complex. And what I have to tell you is how to do the bracket. So if I have a bracket of something from here, tensor here, with something from here, tensor here, you just bracket on the Lie algebra side and product on the maximal ideal side. So the point is that this is commutative, and so it will, or commutative up to sign in the correct way, which means that the differential graded product here will give you the differential graded bracket on L will give you a differential graded bracket here. And so now maybe I should just go to a new blackboard because this is an important. And we defined the Maurer-Cartan functor associated to L to be the set of X in L tensor MA of degree 1 such that the X plus 1/2 X bracket X is 0 in the degree 2 part. And you can prove that this is a pre-deformation factor. So these are all nice properties. And why is there the pre? When I'm going to define a deformation factor, and so where did I put it? Yeah. So I want that for any acyclic, so and then there is a proposition. Let F be a pre-deformation factor from the art to sets. Then the following are equivalent. So condition 1 is in the step 3, the map is an isomorphism. In condition 3, Fa to Fp is a bijection. And then we have condition 2 is that F factors via K of the art, so that homotopic maps give the same map. And what is the third condition? Okay, I did not write it. Maybe I didn't like it so much. So in the moment, I will just keep these two. And if these two are true, in such a case, F is called a deformation factor. And so these deformation factors are the stuff which we really want to study, and it's the stuff which will be controlled very well by differential graded Lie algebras. And well, we can ask ourselves, okay, nature gives us a lot of pre-deformation factors. How do we get a deformation factor? And here you should take comfort from the name. The relationship is precisely like the relationship between pre-sheaf and sheaf. If you have a pre-sheaf, there is a natural way, it's not in general a sheaf, but there is a kind of a best way to make it into a sheaf. And so proposition for any pre-deformation factor F, there exists a natural transformation f to f plus with f plus a deformation factor, such that for any transformation f to g with a g deformation factor, there exists a unique factorization f to f plus to g. And of course, this implies that f plus is essentially unique up to canonical equivalence. And in fact, the point is, once one has this official thing, one can worry how complicated it is, but in fact, it is just given by killing homotopies. So you just take quotient. Okay, so informally, this is not a proof, but the idea of proof is that you quotient f of a, for any a, or f of b if you want, by the equivalence relation which comes from enforcing induced by II. By the way, a reminder, a key point is that if you have two homotopic maps of chain complexes or cochain complexes, then you can always say that one is the other plus something which is homotopic to 0. While here, these are not an abelian category or an additive or anything. So even if you have two which are homotopic, it doesn't make sense to speak of the difference. We cannot just say the image of everything which is homotopic to 0. So we have really to be a bit more careful. I mean, this might be obvious to a lot of you, but this is not obvious to me, and so I say it. Okay, so you can do, if you have something which is close to being a deformation factor, there is a natural way to make it into a deformation factor. And you could ask yourself, well, what about the two examples we just gave? Can we describe the associated deformation factors? And indeed, we can. Okay. So, and example. So if we take the HR we wrote above and take plus, this is just given by hom from R to A in the homotopy category. So the kind of minimum you can expect, how do you make sure that homotopic maps have the same image? Well, in this case, the maps are the objects are maps, and so the first thing you can do is say, okay, this will certainly work. And it turns out it works. And the other example with Maurer-Cartan, it's actually that if we define the formation of L to be Maurer-Cartan of L plus, so the deformation factor associated, then def L of A is equal to Maurer-Cartan of A modulo gauge equivalence. So gauge equivalence is the exponential action of L tensor, the maximal ideal of degree 0. I could write a formula, but I haven't prepared it, and so I'm not going to, but it is again a standard thing that for any Lie algebra, if you take the elements which in degree 1 that satisfy Maurer-Cartan, you can act on them with elements of degree 0 in a suitable way. Okay, and I wanted to finish by giving you one example. I want to say, sorry, before I go on, I haven't yet said. So, definition, if f is a deformation factor, we can define Ti of f. This is just f of c plus c epsilon of I. And again, this is, I think it's I minus 1 to be precise. So this is the grading in the deformation theory grading, so that the tangent is T1. And it is clearly functorial. So it has a vector space structure which is induced exactly in this way, by the same property that you use this, and you can show it has a vector space structure, and with natural vector space structure, and thus functorial. And this is something we need a lot in deformation theory, that the higher tangent spaces, in particular the obstruction space, is functorial. And in fact, one can show that we get really the picture we are used to with obstruction. It does really obstruct stuff. I just don't want to discuss it now. And in fact, and we have another theorem that a morphism f in G of deformation functors is an isomorphism if and only if it's an isomorphism on all tangent spaces. And in particular, this implies that if L to L prime is a homomorphism of differential graded Lie algebras, then def L to def L prime is an isomorphism if and only if L to del prime is a quasi-isomorphism. So it's as unique. This tells you that the differential graded Lie algebra that governs our deformation theory problem isn't quite unique, but it is as unique as it is realistic to expect. And let me give you quickly one example, which is also related to, there will be more examples in the last lecture, but so let me take X in AN an affine scheme. And let me assume, therefore, that X is a spec of some ring S. And remember, today we discussed that there exists a quasi-free resolution. It's not unique, of course, but it certainly exists, with now P in the good ones. And we want to have, there is a natural way which is very similar to how you do in the non-derived, in the classical case, to define a pre-deformation functor for x, really in terms of you associate to every A prime an algebra Ra prime. And we can associate to it a deformation functor def x. And it turns out that theorem def x is naturally isomorphic to def L. So where do I get the differential graded Lie algebra here? I don't have a differential graded Lie algebra. And this is a differential graded algebra. And the answer is I take L as the graded derivations from P to P. If you have a ring, the derivations from the ring to itself are a Lie algebra, an algebra, a commutative algebra, the derivations are a Lie algebra. In this case, P is a graded differential algebra, and so its derivations are a differential graded Lie algebra. And you can do this whole construction, and it's clear that this is not unique, but it's unique up to quasi-isomorphism, and so we have a complete control over what is happening. So this is the general picture, and on Thursday we will see more examples of such differential graded Lie algebras, and we will mention that in fact differential graded Lie algebra is a strong assumption, and we can associate the deformation functors to weakening of the condition. So you can go from differential graded Lie to L infinity, or you can go to something which is called, I think, semi-cosimplicial. I will not talk about that. I will just mention it because it's not something I'm comfortable with. But the point is, as soon as you have some kind of way to make a Maurer-Cartan equation, you get a functor, and this functor up to gauge is a deformation functor and can be used. So what you should think of as all these blackboards is infinitesimal study of derived moduli spaces and derived moduli stacks. And it's done without using spaces. Why do we still want spaces? Because we want global objects, but conversely, once we know the spaces exist, we can study them near each point using this method. Thank you.
Right, any questions? Yeah.
Yeah, just, is it I or I minus 1 in the definition of the TIF?
Yes.
Yes.
Can you, sorry, can you ask the question?
Yes. Is it I or I minus 1 in the definition of TIF?
As the point is that what you want. So usually, in some sense, the natural definition to my heart would have an I. But you need a shift, I think, to get the correct result. If you want that the tangent, you see, you want the T1 is the usual one, is given by C of epsilon mod epsilon squared. So it's a matter of how you number it. What I want is that, as traditional in deformation theory, T1F is F of C epsilon mod epsilon squared, classical, so this degree is 0. And that's why I want a shift by 1. And for instance, I want that T2, which is my obstruction, to be f of c plus c epsilon 1, which means that this epsilon is in degree -1, so I don't have to insist that epsilon squared is 0 because it's odd degree, but as already remarked by Mauro, I also insist that the differential is 0. Here I also insist that the differential is 0.
So what would look the functor like what could be the lift of a morphism to T2, for instance?
I'm sorry, I haven't understood.
Sorry. Without the microphone? No, I don't have the right to do that. What could be, what does the functor look like? So, which data of a morphism the functor taking into account? Like, if you lift a morphism to T2, for instance, what?
I think maybe it's better if we wait the next lecture for this question, and maybe you can ask me with some calm during it's 2 days until the next lecture, and then I can prepare a coherent answer, and I'm sure there will be many other people interested.
Okay.
Thanks a lot. Maybe I have a related question, but when I'm thinking about these TIs, we have a nice interpretation as the T1 as this tangent space and the T2 the obstruction space. For example, if I think about deforming associative algebras, and you have the Hochschild complex, and then we know that these obstructions to lifting to formal deformations lives in the T2. Does this give us, to some extent, an interpretation of what the higher Hochschild cohomology groups do?
It should be, but remember that the higher things are really related to this differential graded stuff. In fact, basically at every level, you can see that Ti as either a tangent for that level or as an obstruction for the level 1 less. So just like the T2 is an obstruction when you try to deform in degree 1 less, then the T3 is an obstruction when your deformation takes place here, and so on. So in that sense, they all have an interpretation, but to interpret it that way, you have to allow yourself this graded structure.
Could then perhaps, for example, if we think about the deformations, the formal deformations are sort of obstructed by the things in T2, then would deforming over the formal power series where we take this T not anymore in degree 0, but degree -1, and then you have T2 and T3 playing.
Yes.
Should I think
yes,
about it like
you
this?
should think about that, and possibly with a T2, the T1 acting via exponential or acting somehow, just as in the case we have, the classical case is that T2 is an obstruction. Once you can do the lifting, T1 tells you what are the choices, but they aren't quite all the choices because of the level before.
Okay.
That some of them get cancelled out by reparametrizing, so to speak, what was happening.
Okay, thanks.
And I think this extends at every degree.
It's very interesting.
No. Sorry. Thank you.
For that blackboard, you wrote that H composite with the T values to 1 is F,
Yes.
and T value to 0 is G. So, but you also wrote in the middle, DT value to 0. So this.
Oh, I probably made a mistake.
Oh.
I think I swapped a 0 to 1 in one of the two.
So erase the middle one, you mean?
Okay, let me bring this down.
Or
No, it's the other one. Sorry. Yes, so the first thing I want to say is that here I definitely had the other way around in mind. Actually, I think I had the other way around in mind, not here, but here. And notice that this is really a homotopy. You get a map for every value of t. You can give t any number. So you really have a one parameter family with these two. Okay, sorry. Is there still a question?
So, but there is a third one, dt value to 0. This
Yes.
is the one.
Well, the point is this is the topology picture. This I said but didn't write. This is the model we use. This is how I remember what I want to do. This is the case where these are topological spaces. And so the point with the dt is that the dt, if I send the t to 0, it's clear that dt has to go to 0. Because what is the differential of 0? And whatever number, if I send the t to a scalar, I mean, that we can have a lot of things, but we always want that the differential of the constants is 0.
Oh, I see.
And so this tells you, it's actually, I think, a consequence of the axioms that the differential of 1 is 0, right? Because you have that the differential of 1 times a is the differential of, yeah, let me write it like this. This is of 1, and so it has to be 0, right? So this means that, and for now linearity, you get that d is linear, so the differential of every complex number is 0, and so if you map t to a complex number here, then the dt has to go to 0, otherwise you don't even get the map of differential graded algebras.
Yes. Thank you very much.
Okay, so let's thank Barbara again.